video, we're talking about how to take the equations of quadric surfaces and put them into standard form, and then how to use the standard form to identify which quadric surface it represents. So in this first example, we have the equation y squared equals x squared plus z squared divided by 9. So when you have the equation of a quadric surface, you're looking at a couple of important things. First of all, which variables are involved in the equation? Sometimes you're only going to have x and y, but oftentimes you'll have x, y, and z. That's going to affect the type of quadric surface you're dealing with. Then also you're looking to see whether or not your variables are first or second degree variables. So a first degree variable would be like this one right here, y to the first power, or just y. If the variable is squared, then it's a second degree variable. So in this case, we have 3 second degree variables because we have y squared, x squared, and z squared. You're also looking to see how many variables are on one side of the equal sign together versus by themselves on the other side of the equal sign. So in this example, we have one variable by itself on the left, 2 variables grouped together on the right. That's going to make a difference. And then depending on the arrangement of the variables, what are their signs? So sometimes the signs will be positive and sometimes they'll be negative. In this case, with the y on one side by itself and the x squared and z squared together on the other side, all of the signs are positive. So we have a positive y squared, a positive x squared, and a positive z squared. With all of that in mind, what we can do is go over to our chart of quadric surfaces. And this is only part of the chart, but what it shows us is that we have this second column here that shows the standard form of each of the quadric surfaces. Take, for example, the first row here, the standard form for the ellipsoid. What we notice in the standard form for the ellipsoid, and we're looking at this equation right here, we see that we have x squared, y squared, and z squared all together on one side. So we have all 3 variables, x, y, and z. They're all squared, they're all second degree variables. All of the signs are positive. We have a positive x squared, positive y squared, and positive z squared when all of the variables are on one side of the equal sign together. Remember, in our equation, we had one of the variables separated onto the other side of the equal sign. In our case, our equation is going to look more like the standard equation of a cone, because if we look at this standard equation, what we notice is, again, all 3 variables, all of them are squared, x squared, y squared, and z squared. But in the standard equation of a cone, we have one of the variables isolated on one side of the equal sign by itself, and the other 2 grouped together on the other side of the equal sign. And when they're arranged in that way, all 3 variables are positive. That matches the form of our first equation. So what we can say is that our first equation here is the equation of a cone. What we know from the chart is that the axis of the cone is set by the variable that's by itself. So because in our case y is by itself, that means that this cone is going to open up along the y-axis. If x were by itself, the cone would open up along the x-axis, and if z were by itself, the cone would open up along the z-axis. Furthermore, because we have this denominator here, this 9, under the z squared, it tells us that this is an elliptical cone or an elliptic cone, because this value here of 9 is going to stretch the cone out along the z-axis. Because the 9 is paired with the z squared, it's going to stretch the cone out along the z-axis so that the cone is taller than it is wide, and it's going to open up along the y-axis. If we look at our second equation here, we have x squared plus 2y minus 2z squared is equal to 0. Notice here that we have 2 second degree variables, x squared and z squared. We have 1 first degree variable, we have y to the first power. Oftentimes when you have a single first degree variable, it's helpful to get that variable by itself on one side of the equal sign. So what we'll do is we'll keep the 2y on the left. We will add 2z squared to both sides, so 2z squared, and we will subtract x squared from both sides, so minus x squared. If we then divide both sides by 2 to solve for y, what we get is y is equal to, the 2 will cancel with this 2 here, and we'll just be left with z squared, and then we'll have minus 1/2 x squared, or minus x squared over 2. In this form, then, what we notice is that we have the first degree variable by itself on one side of the equal sign, and then we have 2 second degree variables on the other side. One of them is positive, the z squared is positive, and the other one is negative, the x squared is negative. So we're looking for that same form when we go back and look at our chart. And where we find it in the standard form column is here in the last row. where we see that the standard form of a hyperbolic paraboloid includes two second-degree variables on one side of the equal sign, where one of them is positive and one of them is negative. Notice here in the standard form that x squared is positive and y squared is negative. And then we have that equal to a first-degree variable on the other side of the equal sign. So what we can do is call this equation the equation of a hyperbolic paraboloid. And if we want to give more information about the paraboloid, we know that it opens along the axis set by the first-degree variable. So because y is by itself, and that's the first-degree variable, this hyperbolic paraboloid is going to open up along the y-axis. The other thing we know is that the value in the denominator with this first-degree variable, in this case, our denominator is 1, this is y over 1, the value right here determines whether the hyperbolic paraboloid opens up or down. If this value in the denominator is positive, the hyperbolic paraboloid opens up. If it's negative, it opens down. So because ours is positive, we can say that this is a hyperbolic paraboloid that opens up along the y-axis. If we look at our next example, this one's a little more complicated. What we want to do is group together our variables, so all the x's will go together, all the y's together, and all the z's together, and we want to complete the square with respect to each variable. So if we pull out here, we have 4x squared. That's the only x variable, so we'll leave that by itself. For the y variables, we have y squared minus 4y. For the z variables, we have 4z squared minus 24z, and then we'll go ahead and subtract 36 from both sides to get negative 36 over here on the right. Now we want to complete the square with respect to both y and z. Before we can do that though, before we can complete the square, we need to make sure that the coefficient on both the y squared and z squared terms is 1. We already have here 1y squared, so we're fine there, but we have 4z squared. So what we want to do is factor out a 4. If we factor out a 4, then we'll get just z squared. So what we'll end up with is 4 times z squared. But because we factored out a 4, we get 24 divided by 4 is 6. So we end up with a minus 6z. Now we have a coefficient of 1 on both the y squared and z squared terms. So we can work on completing the square. And when we complete the square, we take the coefficient on the first degree variable. So we take, in the case of y, we take negative 4. And we take negative 4 and we divide it by 2. The result is negative 2. And then we take that result and we square it. And the result there is 4. Which means what we want to do is add 4 to our y squared minus 4y in order to make this a perfect square. But because we're adding 4 to the left-hand side of our equation, we also have to add 4 to the right-hand side in order to keep the equation balanced. And now we'll do the same thing for z and get it all done in one step. So we take the coefficient on our first degree z variable. So the coefficient is negative 6. So we take negative 6, we divide it by 2. The result is a negative 3. And then we take that result and square it, and the result of that is a positive 9. So then we want to add positive 9 to the left, and here we have to be really careful because you might just say we have to add positive 9 to the right in order to keep the equation balanced. However, because we're adding 9 inside of the parentheses, and this 4 here in front of the parentheses has to be distributed across every term, when we add 9, it's like we're adding 9 times 4, or like we're adding 36 to the left-hand side of the equation, which means we also have to add 36 to the right-hand side of the equation. So now when we simplify, we're going to get 4x squared. Y squared minus 4y plus 4 factors to y minus 2 quantity squared. We have plus 4. And then z squared minus 6z plus 9 factors to z minus 3 quantity squared. Over here on the right-hand side, a negative 36 and a positive 36 will cancel with one another, so we're just left with 4. Then we want to go ahead and divide through by 4 because we don't want these coefficients in front of our x squared, y squared, and z squared terms. Denominators are fine in terms of putting the equation in standard form, but we want to get rid of these coefficients. So when we divide through everything by 4, what we get is x squared plus, we'll get y minus 2 quantity squared divided by 4. We'll cancel this 4 and we'll just be left with z minus 3 quantity squared, and then 4 divided by 4 is 1. Now that the equation is in standard form, we notice we have all three variables, of course, x, y, and z. All three of them are squared. We have an x squared, a y squared, and a z squared term. They're all together on one side of the equation, and they're all positive. We have a positive x squared, a positive y squared, and a positive z squared. So when we go back to our chart to look for something that matches that form, what we find is, again in the first row here, the standard form of an ellipsoid. We see here that we have x squared, y squared, and z squared all together on one side of the equation. They're all positive. We have a positive x squared, positive y squared, and positive z squared. And so we know that this is the equation of an ellipsoid. So we can go ahead and call this an ellipsoid. And if we wanted to give more information about it, what we can do is grab from our standard form equation these values here. We have y minus 2, z minus 3, and if we realize here that this x squared, we could call it instead x minus 0 quantity squared. And if we grabbed here the 0, so we have x minus 0, y minus 2, and z minus 3, if we have the standard form equation in that form, then we can say that the center of the ellipsoid is given by the coordinate point 0, 2, 3. So this is an ellipsoid with its center at 0, 2, 3, which means it's shifted off the origin. And then if we look at our last example, it's going to be similar to this one we just did in the sense that we want to complete the square with respect to each variable. So if we group all of our x terms together, we have x squared minus 4x. We have a minus y squared minus 2y. If we factor out that negative sign, we end up with a minus y squared plus 2y. And then if we group our z terms together, we end up with a plus z squared minus 2z. Subtracting 4 from both sides, we end up with a negative 4 on the right. And then again, with respect to each variable, we want to complete the square. The coefficients on x squared, y squared, and z squared are all 1, so we can proceed with the same thing we did before. We know negative 4 divided by 2 is a negative 2. Squaring that value, we get a positive 4, so we want to add 4 over here, which means we also want to add 4 over here. Then for y squared plus 2y, we take the 2, we divide that by 2 to get 1, we square that to still get 1, and so we're adding 1 here. But keep in mind, because we have this negative sign out in front, adding 1 inside the parentheses is like subtracting 1 when we distribute that negative sign to it, which means we have to subtract 1 over on the right. And then for z, taking our negative 2, dividing it by 2, we get a negative 1. Squaring that value, we get a positive 1, so we end up with positive 1 here, and then we want to add 1 over on the right. So then if we factor on the left-hand side, x squared minus 4x plus 4 factors to x minus 2 quantity squared. Y squared plus 2y plus 1 factors to y plus 1 quantity squared. Z squared minus 2z plus 1 factors to z minus 1 quantity squared. And then over on the right, we get positive 4 to cancel with negative 4, and negative 1 to cancel with positive 1, so we have equals 0 over on the right. When we're dealing with standard form, we usually want to get all of our signs positive if we can. If we were to add this quantity y plus 1 squared to both sides, we would cancel it over here, and we would end up with a positive quantity y plus 1 squared over on the right-hand side. So let's go ahead and do that. What we'll end up with is x minus 2 quantity squared plus z minus 1 quantity squared is equal to y plus 1 quantity squared. So now everything is positive. We have a positive x, positive z, and positive y terms. All the terms are squared, and we have two variables together on one side, one variable on the other side by itself when all the terms are positive. So looking back at our chart, here we can see that we have x squared, y squared, and z squared, so they're all squared variables, with two of them on one side and one of the variables on the other side when all of the signs are positive. So again, we can go ahead and call this last equation a cone, but unlike this first cone, which was an elliptic cone because of this 9 in the denominator with the z squared, here in this cone we have this value over 1, this value over 1, and this value over 1, and when all of those denominators are equal, we can call it a circular cone. So because those are equal, this is a circular cone versus this would be an elliptic cone. And that's how you put the equations of quadric surfaces in standard form to identify their figures.